Okay, in this video, we are going to derive the special ratios that go with the 30-60-90 and the 45-45-90 triangle, and then we'll also talk about the trig ratios that go with that, and we'll just kind of work our way through the sheets and talk our way through this. So right here, this special right triangle worksheet. This figure shows an isosceles right triangle. What is the measure of each base angle? How do you know? Okay, if we have an isosceles right triangle, by the base angles theorem, with isosceles triangles, angles that are opposite equal sides are equal. So we have two equal angles here, since both of these are x, and two equal angles that make up 90 degrees, along with the 90, which gives us a triangle sum of 180. Means that each one of these has to be 45 degrees. So each base angle measures 45 degrees. Okay, how do we know? We can use base angles theorem. And two congruent complementary angles means each one is 45 degrees. So we have congruent, complementary. Remember, complementary adds up to 90. Angles. So we have congruent complementary angles. So that means each one's got to be 45. Okay, so maybe a little bit different wording, but that's kind of the basic idea. Okay, part B. Let the legs of the right triangle have length x. Okay, they've got it labeled there. You can use the Pythagorean Theorem to find the length of the hypotenuse in terms of x. So a squared plus b squared is c squared. They're using AB instead of C. So and this is a squared plus b squared is equal to c squared, Pythagorean theorem. The distance from A to B is the same as C. I just labeled C on here. So x squared and x squared is 2x squared. And if we want to find out what AB is, we have to do the square root of both sides. So the square root of AB squared comes out as an AB. The square root of 2x squared comes out as root 2 times x. The square root of x comes out as an x, and root 2 can't be simplified. So the square root of 2x squared is root 2 times x. So the hypotenuse is root 2x. If the sides are x, the hypotenuse is root 2 times x. A student claims that if you know one side of an isosceles right triangle, then you know all the side lengths. Do you agree or disagree, and why? So on this one, let's kind of look at some ideas here. Okay, if you know one side length, so if you know one side length, let's say this is a 7. You know that this is going to be a 7 because it's isosceles. And you know that from the Pythagorean theorem, this is going to be the root 2 times 7. So it's going to be 7 root 2. X radical 2. So if you know a side length, you do know all the sides. Now let's look at the other case where maybe we're given the hypotenuse. Let's say the hypotenuse is 14. If I do 14 divided by root 2, since the side times root 2 made the hypotenuse, or makes the hypotenuse, if I do 14 divided by root 2 and rationalize it, it gives me 14 root 2 over 2, which is 7 root 2. Each side length must be 7 root 2. If this is 7 root 2, root 2 times 7 root 2 is 7 root 4, which is 7 times 2, which is 14. And since it's isosceles, right, this other side must also be 7 root 2. So yes, this kid is right. If you know one side length in an isosceles right triangle, you know enough to find all the side lengths. So it says explain. So I kind of explained my way through here. Basically, side times root 2 equals hypotenuse, or hypotenuse divided by root 2 equals side. And sides are congruent, or legs are congruent. Call it leg. Legs are congruent. So those are the three main ideas that go with that one. Okay, let's look at 1b. Explain how to find y in the triangle at the right. So let's see what we got. Looking at this, we have an isosceles right triangle with this big triangle, which means that this AB distance must be square root of 2. Because we've got 1 times radical 2. In this other triangle here, though, let's see what we got. So this is a 45, and this is a 45 because it's isosceles right. Now this altitude in this isosceles triangle is going to divide the base. So each one of these is going to be root 2 over 2. And it's also going to bisect this vertex angle. The altitude is going to bisect the vertex angle. If this was a 90, this is going to be a 45. So we have two smaller 45-45 triangles made by this altitude. And we need to find out what y is. So let's see. So from the altitude being the bisector of the base, and from the first triangle knowing that 1 radical 2 are the ratio of the side lengths, we found that one of the sides is root 2 over 2. That means that y must be congruent to that. Y must also have a length of root 2 over 2. Okay, so explain how to do this. Okay, so triangle ACB is isosceles. Triangles ADC and BDC are, okay, ABCB is also 45-45-90. Are 45-45-90s also. Let's see, so altitude of triangle ACB bisects AB, segment AB. So if from the original triangle, if the length of AB, no bar above it, is equal to root 2, then DB length is root 2 over 2. Because DCB, triangle DCB, is isosceles, then side DC is congruent to side DB, and DB is equal to DC in terms of distance, and DC, therefore DC equals y, which equals root 2 over 2. So it's kind of like a long, drawn-out explanation, but those are pretty much some of the steps in the reasoning behind that. Okay, let's go to the next page. So this mainly dealt with the 45-45-90 triangle, and what we're supposed to basically get out of that is this idea that in a 45-45-90 triangle, your basic side lengths are 1 radical 2. So if this is a 7, this is a 7, this is 7 radical 2. If this is a 14, 14 divided by radical 2 is going to be this one, and this is also going to be 14 divided by radical 2. So sides times radical 2, hypotenuse divided by radical 2. That's how you can work back and forth between those. So let's look at this next page now. Now this is going to set up our 30-60-90 triangle. So it says in the figure, triangle ABD is an equilateral triangle, and BC is a perpendicular from B to AD. So since this is an altitude, it's a perpendicular, which is an altitude in an isosceles triangle, and altitude is the perpendicular bisector of the base. Explain how to find the angle measures in triangle ACB for part ABD for part 1A here. If this is an equilateral triangle, equilateral triangles have equal sides by definition, and opposite, and by the base angles theorem, sides that are opposite equal sides are equal, or angles that are opposite equal sides are equal. So we have three equal angles that must be 180 degrees. Each one of these angles must be a 60. So angle B, angle ABD, is a 60-degree angle. Now, one of the properties of an altitude in an isosceles triangle, to be isosceles, these two sides need to be congruent. The altitude bisects the base, and also the altitude bisects the vertex angle. So that makes that a 30-degree angle up there. So explain how to find the angle measures in ABC. Equilateral is equiangular. Which means that all the angles are 60 degrees all the way around. Altitude bisects, because we're only worried about angle measures for this one, bisects vertex angle. So this 60 gets divided into 30, into 2, so you get 30. So we got a 60, a 30, and the altitude's perpendicular, so we got a 30, 60, 90. So out of this triangle here, we've got a 60, we've got a 30, and we have a right angle there. Okay, explain why triangle ACB is congruent to triangle DCB. There's a couple of different things we could think about on this. Between these two triangles, this side, this BC, is reflexively congruent to both sides. It's part of both triangles. We were told that this was an equilateral triangle, so BA and BD are congruent to each other. And let's see what else we got. So this gives us hypotenuse leg if we want to prove, if two right triangles, both these are right triangles. We've got hypotenuse leg pattern. So some geometries will let you use hypotenuse leg. The other thing we can do is the altitude bisects the base. So those are both going to be congruent to each other. And if the altitude bisects the base, then we have these two sides congruent. And we could actually do side, side, side. Hypotenuse, this is reflexive, congruent with itself. These two are congruent because of the altitude bisecting the base. So side, side, side pattern would be something we could use. We could use, I already said we could use hypotenuse leg as a right triangle. Two 90-degree angles are congruent to each other. We could do side angle side. And this 60 is congruent to this 60. This 90 is congruent to that 90. And that's reflexive, congruent to itself. That could be an angle angle side. Angle angle side could also work the other way, 60 to 30 to side. And let's see what else we got. Side, side angle side. We got angle angle side, side angle side, 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 side. So those are different ways we could use. We could do leg leg. This is congruent to this by the bisector. This is congruent to itself. So in right triangles, there may be a leg leg theorem that you can use depending on your geometry. So those are all different ways that we could use to explain why those two triangles are congruent to each other. Okay, let the length of AC be x. So what I did over here was I kind of sketched this triangle by itself. I did like an auxiliary diagram thing. So ACB triangle here. Let the length of AC be x. What is the length of AB going to be? Well, if this is x, we already saw that this bisected this base, which was congruent to these other sides, by 2. It bisected the base in half. So if this is x, this must be x by the congruent triangles. And if this is 2x, because it's equilateral, each one of these must be 2x. So basically we can argue that AB must be 2x. And what would the argument be for that? I guess we could say corresponding parts of congruent triangles are congruent, maybe, or some other argument, something something along those lines. D, in the space below, show how to use the Pythagorean theorem to find the length of BC. So we want to find this length of BC using the Pythagorean theorem. If this is 2x, and that's the hypotenuse squared minus the side squared is going to give us the other side squared. So 2x squared minus x squared makes BC squared. So c squared minus a squared equals b squared. That's what we're doing here. Okay, 2x squared, 2x quantity squared is 4x squared, minus x squared gives me 3x squared. That's equal to bc squared. To find bc, take the square root of both sides. bc is going to be x times the square root of 3. So if this is x, we already saw that this is going to be 2x, and now we're seeing that this is going to be x times the square root of 3. So if we have basic side length ratios here, if this was a 1, this would be a 2, and this would be a 1 times radical 3. That would be a radical 3. So this is where we get our basic 30, 60, 90 ratios from. Now this is 60 there, that's a 30 there. 30 is opposite the short side, 60 is opposite the longer leg, and the hypotenuse is double the short side. What's the ratio of the side lengths in a right triangle with acute angles that measure 30 and 60? We've basically got 1 radical 3, 2 from smallest to least to greatest. Opposite the 30, opposite the 60, opposite the 90. Okay, 2B error analysis. A student drew a right triangle with a 60-degree angle and a hypotenuse of length 10. Then he labeled the other side lengths as shown. Explain how you tell just by looking that the student made an error. Okay, so based on what we were talking about here, the hypotenuse is twice the short side. Got that. And the other leg, the medium size side of the triangle, is root 3 times the short side. Now what he has is root 3 times the hypotenuse. This should actually be 5 root 3. So that's where the error was. Should have used short side times root 3 for LK, the distance from L to K. Okay, let's look at the next page. That's where the fun stuff comes in. So let's see what we got. So the right triangles investigators sometimes are usually called special 45, 45, 90 and 30, 60, 90 triangles. Use your previous work to fill in the missing side lengths. If this is a 1, this is a 1, this is 1 times square root of 2. If this is a 1, this is 1 times square root of 3, and this is going to be twice the short side. So this set of triangles is very useful. You should be able to sketch it anytime you need it, or else memorize this chart that we're going to fill in. So, and we're talking about sine, cosine, and tangent. Sine, using some old hippie, came around here to offer apples. Gives us a mnemonic way of remembering what goes with sine, cosine, and tangent. Sine is opposite over hypotenuse, cosine adjacent hypotenuse over hypotenuse, tangent opposite over adjacent. We can fill these in and then simplify. So for 30 degrees, We're up here. The sine is opposite over hypotenuse, 1/2. The cosine is adjacent. Now, remember opposites, if you're using your reference angle, the hypotenuse is always opposite the right angle. Then you got to think about adjacent versus opposite with the other legs that are left. Opposite the 30 is the side you can't touch if you were standing at the 30. The side that makes the 30 up is the adjacent side. So for cosine, we have adjacent over hypotenuse. We have √3/2. And tangent is opposite over adjacent. We have 1/√3, which we have to rationalize to √3/3. Okay, let's look at 45. For 45, we're using this triangle. Sine is opposite over hypotenuse. We get 1/√2, which simplifies to √2/2. For cosine 45, we have adjacent over √2, same thing, √2/2. And tangent is opposite over adjacent, opposite over adjacent. We get 1/1, which is 1. Let's go to our 60 line. For 60 now, we're using this angle. So now the opposite side is the √3, the adjacent side is the 1, and we still have 2 as the hypotenuse. So for sine, we're using opposite over hypotenuse. Using the 60 as our reference, opposite √3, hypotenuse is 2. For cosine, we've got adjacent over hypotenuse. It's going to be 1/2. And for tangent, we have opposite over adjacent. We have √3/1, which is √3. So here we have the sine, cosine, and tangent ratios that go with 30s, 45s, and 60s. Now these angles occur because these are easy to find and easy to memorize. In engineering, you see a lot of 30, 45, and 60-degree angles in like roof trusses and in like wall bracing and things like that, bridge supports, because these are easy to calculate and easy to fabricate, you know, a whole bunch of the same lengths without having to do measurements or anything like that. Okay, 3a, what patterns do you see in the sine and cosine columns? So let's look. Okay, for 45, the sine and the cosine is the same. And that kind of makes sense because A and B are both congruent, so opposite and adjacent are kind of all relative, but they're going to be the same numbers. So that's why those were the same. What's going on with the 30 and the 60, though? Notice that 1/2 for sine of 30 is the same thing as 1/2 for cosine of 60. And this goes back to the idea that if you have a 60, the opposite side is √3. If you have a 30, the adjacent side is √3. So adjacent goes with cosine, opposite goes with sine, and that's the reason these switch places. And we see the same thing with cosine and sine, cosine of 30 and sine of 60. You're basically flipping your reference sides from opposite to adjacent and adjacent to opposite as you're doing these. So sine of 30 is the same thing as cosine of 60. Sine of 30, opposite over hypotenuse, is the same as cosine of 60, which is adjacent over hypotenuse. But the adjacent to the 60 is the same as the opposite to the 30. Okay, so those are the patterns. Sine 30 equals cosine 60. Cosine 30 equals sine 60. And sine 45 equals cosine 45. Those were the three things that we noticed from that. Okay, 3b, for which angles is the tangent ratio less than 1, equal to 1, or greater than 1? So we're talking about tangent. We turn these into decimals. the square root of 3 is 1.73. We got a 1.00 there for that one. And root 3 over 3, the square root of 3, square that. The square root of 3 divided by 3 comes out to be 0.5773. Okay, I think I might have messed up on this. Let's look at this. Tangent of 30. I was in a hurry for this, I guess. Tangent of 30 is 1 over root 3. We actually root 3 over 3, so we get 0.577. So in terms of for which angles is the tangent ratio less than 1? It's less than 1 for root 3 over 3, which is 30 degrees. For equal to 1, 45 degrees. And for greater than 1, we have 60 degrees. That's what they're looking for that section. Okay, so I hope this kind of maybe helped sort of do like an investigative type argument for where the special ratios come from for 45-45-90s and 30-60-90s. The classic, proof basically for 30-60-90 has to start with an equilateral triangle, because that gives you the 60s and the 30s that you need when you drop the altitude. And then we use Pythagorean Theorem, with some arbitrary number for the short side. We can use Pythagorean Theorem and see what all the other sides need to be and everything. So let me know if you have any questions on this, or if there's something else that you want to see worked, let me know.